Okay, so now we have defined covariance, okay, and another very important property or result that we want to talk about is how zero covariance is related to independence, okay? So one thing, okay, very important to note, and I was hinting it earlier when we introduced the covariance expression of x, y earlier as well, is that if x and y are independent, okay, what we know, okay, if you remember, is that covariance of x, y, right, is the expectation of the product minus the product of the expectation. If they're independent, remember, we're able to break the expectation into the product as well. Okay, so that will give you a zero covariance. Okay, so what this does tell us, okay, is that if x and y independent, then their covariance is zero. Okay, and the reason is because we're able to break, right, the product, the expectation of the product into a product of the expectations. Okay, and then we're actually further able to extend this to n different random variables. Okay, so if x1, x2 up to xn are independent, then the variance, okay, of the sum is the sum of the variance. Okay, and that is because if you remember, if we don't know whether they're independent or not, we have that, remember, covariance of xn, xi, and xj, right? That was from previous video, okay? And then all of them become zero because they're independent, okay? That's why you can get rid of all of the zeros there, okay? All right, so notice, okay, we highlight, this is only one way, okay? Meaning that x and y independent, you know that the covariance is zero, okay? However, covariance equals to zero does not mean that they're independent. Okay, so that, or another highlight I want to make over here is that the covariance equals to zero is not a sufficient condition. Okay, whenever you're trying to show x and y are independent, you have to go back to the definition of their being dependent, right? The joint CDF is the product of the marginal CDF, or the joint PMF is the product of the marginal PMFs, or the joint CDF is the product of the marginal PDFs. Okay, so counterexample. Okay, let's take a time to think about what a counterexample could be. So now I'm telling you, okay, x is uniform, negative 0.5 to positive 0.5, okay, and then y is x squared, okay. So clearly, I mean, even without thinking about it, like we will go ahead and find the covariance just to get the practice to do that covariance calculation. But notice, like the question asks also, and decide if x and y are independent. Okay, so well, independence, if you think about it, like y is x squared, right? There's no way they're going to be independent because y depends on x, it's x squared, okay? However, like I said, this is a counterexample. So if we do the math, we're going to realize that the covariance is actually zero, okay? So let's see how we can get it. So covariance, let's see. So we need to get, so remember, covariance is expectation of x times y minus the product of ex and ey. So we need to get, in this case, the expectation of x and the expectation of x times y, okay? And to do that, let's do it step by step, okay? So the covariance calculation, okay, expectation, okay, of this is gonna be zero, okay? If you do the math, you will realize it's zero, but also notice we know the result, right, of a uniform. The expectation of the uniform is the upper bound minus the lower bound divided by 2, okay, in this case, oh, sorry, a plus b, the upper bound, the lower bound plus the upper bound divided by 2, which is going to be the mean, which is 0. Okay, but also, well, if you think about it, it's centered, right, at the middle point is 0 in this case. So the expectation of x is 0. Okay, and so for us, another thing we need to do, right, is to find the expectation of x times y. Okay, and x times y, as you can see over here, is becoming expectation of x cubed. Okay, and then for that, as we know, we are working with x cubed, right, as the uniform. So uniform, the PMF here is the difference of this two is 1, right? So this becomes integrating x cubed, okay, from negative 0.5 to positive 0.5, which becomes 0. Okay, and you can do so for expectation of x squared as well. Okay, I'm omitting that result over here, but you will show that, well, actually, let me put it this way. It's not necessary to show a expectation of x squared because the expectation of x is 0 already. So if I'm going back to the covariance expression, right, I have expectation of xy minus the product of the expectation. So it's expectation of x cubed minus expectation of x times expectation of x square. So regardless of what expectation of x squared going to be, this is 0. So this is canceled, becoming 0. It's becoming 0. So that is 0. Okay. So if you want, you can just do that extra practice, right, to get the expectation of x squared work. But it's not necessary in our case. Okay. All right. So we are arriving the result, right? The covariance is 0. Okay. But just like I was saying earlier, they're not independent because y equals to x squared. Okay. So if we focus on that statement, one thing I would just say that because like in this particular case, you can just say that y is x squared, so they're not independent. But more formally, as we know, okay, we need to show that the fx, the joint, right, is not the product of the marginal over here. Okay, so this is certainly a little bit hard to show in this case. Okay, so that's why I mean it's totally okay if you recognize that y equals to x squared. Okay, when I say it's a little bit hard to show, is because I guess we would need to know the joint first. I don't think it's given to us. Okay, we know the marginal each. Okay, but like I said, y equals to x squared. So you know that they're not independent in this case. It just happens that the covariance is 0. Okay, so this is the counterexample of what we're saying over there. So again, the sufficient condition for independence is not like covariance equals to 0 or like the expectation of the product is the product of the expectation. They are true because they're independent. Okay, but when they're true, you cannot say that x and y are independent. You always need to go back to the definition to show if they're independent or not. Okay.